Imagine stepping outside tonight and looking up to find the moon completely gone. Not hidden behind clouds, not in a new moon phase, but completely erased from existence. What you'd see would blow your mind and fundamentally change everything you thought you knew about the night sky above us. Right now, as you're watching this, the moon is quietly stealing light from billions of stars you've never seen. It's washing out entire galaxies, hiding cosmic events that happen once in a lifetime and blocking your view of the most spectacular light show in the universe. But what if we could turn off that celestial streetlight for just one night? What secrets would the darkness reveal? Stay with me because by the end of this journey, you'll never look at the night sky the same way again. Most people think they know what the night sky looks like. You step outside, maybe see a few dozen stars on a clear night, spot the Big Dipper if you're lucky, and call it good. But here's the thing that keeps me awake at night as an astronomer. You're seeing maybe 1% of what's actually up there. The moon, that beautiful silver disk we all love to photograph, is essentially acting like a massive floodlight pointed directly at the most incredible show in the universe. Think about it this way. If you tried to watch a movie in a brightly lit room, you'd miss all the subtle details, the background characters, the atmospheric lighting that makes the film magical. The moon is doing exactly that to our cosmic movie theater. It's not the moon's fault, it's just doing what moons do, reflecting sunlight back at us. But that reflected sunlight, even from a half moon, is bright enough to wash out stars that are literally millions of times more luminous than our sun. They're just so incredibly far away that their light gets completely overpowered by our lunar neighbor. The average person living in a city might see 30 to 50 stars on any given clear night. Someone in the suburbs might spot 100 or two. But remove the moon from the equation, and suddenly we're talking about thousands upon thousands of stars becoming visible to your naked eye. We're talking about seeing the Milky Way in all its glory, stretching across the sky like a river of light. We're talking about spotting other galaxies with nothing but your eyes. But this isn't just about seeing more pretty lights in the sky. When we remove the moon from our cosmic neighborhood, we're essentially removing one of the most significant factors that has shaped life on Earth as we know it. The gravitational dance between Earth and the moon affects our tides, our weather patterns, the length of our days, and even the tilt of our planet. Without the moon, Earth would be spinning faster, our days would be shorter, and our planet would wobble chaotically on its axis like a spinning top that's about to fall over. The story of what the night sky would look like without the moon is really a story about light pollution on a cosmic scale, about gravitational relationships that span hundreds of thousands of miles, and about how the absence of one celestial body would reveal the presence of countless others. It's a story that begins with understanding just how much light the moon actually reflects, and how that reflection has been shaping human culture, navigation, and our relationship with the cosmos for thousands of years. Let's start with the basics of lunar illumination and work our way up to the mind-bending implications. The moon doesn't produce any light of its own. It's essentially a giant gray rock floating in space, reflecting about 12% of the sunlight that hits it. That might not sound like much, but when you're talking about the sun, even 12% of that enormous energy output is enough to light up our entire night sky. A full moon provides about 0.25 lux of illumination. To put that in perspective, a typical office is lit to about 500 lux, and bright sunlight measures around 100,000 lux. So the moon is pretty dim compared to artificial lighting or sunlight, but in the context of starlight, it's absolutely massive. The brightest stars in our sky provide only about 0.00001 lux. This means the full moon is roughly 25,000 times brighter than the brightest star visible to your naked eye. When astronomers talk about the moon's impact on sky brightness, we use something called magnitude scales. The full moon has an apparent magnitude of about negative 12.7, while the faintest stars you can see with your naked eye under perfect conditions have a magnitude of about plus 6.5. Remember, this is a logarithmic scale, so each magnitude represents about 2.5 times difference in brightness. The moon is literally outshining everything else in the night sky by factors that are difficult to even comprehend. Now imagine all that reflected light suddenly gone. The first thing you'd notice is how incredibly dark everything becomes. Your eyes, which normally adjust to the ambient light provided by the moon, would take much longer to reach their full dark adaptation potential. Human eyes can take up to 30 minutes to fully adjust to darkness, and most people never experience true dark adaptation because there's always some source of light around, whether it's the moon, streetlights, or the glow from nearby cities. In our moonless world, once your eyes fully adjust, you'd start to see layers of the universe that normally remain hidden. The first layer would be the dramatic increase in visible stars. Instead of seeing maybe 2,000 to 3,000 stars on the clearest nights, you'd suddenly be looking at 6,000 to 8,000 stars visible to the naked eye. These aren't just random points of light scattered across the sky. They're organized into patterns, clusters, and formations that tell the story of our galaxy's structure. The constellation patterns would still be there, but they'd be embedded in such a rich tapestry of additional stars that finding familiar shapes might actually become more challenging. It would be like trying to connect the dots in a picture where someone has added thousands of extra dots. The Big Dipper would still be the Big Dipper, but it would be surrounded by so many additional stars that picking it out might require some careful observation. But the real show would begin when you start noticing the Milky Way. Under truly dark skies without any moonlight, the Milky Way isn't just visible, it's the dominant feature of the night sky. It would stretch from horizon to horizon like a luminous river flowing through space, with dark patches and bright regions that reveal the structure of our home galaxy in incredible detail. These dark patches aren't empty space. They're enormous clouds of dust and gas that block the light from stars behind them. The bright regions are areas where millions of stars are concentrated, creating stellar neighborhoods that shine collectively across thousands of light years. From our vantage point on Earth, we're looking edge-on through the disk of our galaxy, which is why the Milky Way appears as a band across the sky rather than a circular shape. The center of our galaxy, which lies in the direction of the constellation Sagittarius, would appear as a bright, bulging region of the Milky Way. This galactic center contains a supermassive black hole with a mass equivalent of 4 million suns, surrounded by some of the oldest and most densely packed stars in our galaxy. Without moonlight washing out these details, you'd be able to see the intricate structure of this galactic core, including dark lanes of dust that create patterns and shapes within the bright stellar backdrop. Moving beyond our own galaxy, the absence of moonlight would reveal other galaxies that are normally invisible to the naked eye. The Andromeda Galaxy, which is already barely visible under perfect dark sky conditions, would become a clearly obvious oval patch of light spanning about 6 times the width of the full moon. This neighboring galaxy contains roughly 1 trillion stars and is currently racing toward us at about 250,000 miles per hour. In about 4.5 billion years, Andromeda and the Milky Way will collide and merge, creating a completely new galactic structure. But Andromeda wouldn't be alone. The Triangulum Galaxy, also known as M33, would become visible as a fainter but still noticeable fuzzy patch. Even more remarkably, keen-eyed observers might be able to spot the Large and Small Magellanic Clouds, two smaller galaxies that are satellites of the Milky Way. These irregular galaxies would appear as bright, cloud-like patches in the southern sky, assuming you're observing from the southern hemisphere where they're visible. The absence of lunar light would also reveal the zodiacal light, a faint glow that extends along the path of the sun and planets through the sky. This ethereal light is caused by sunlight reflecting off tiny dust particles scattered throughout the inner solar system. It appears as a triangular wedge of soft light rising from the horizon just after sunset or before sunrise. Most people have never seen zodiacal light because it's so easily washed out by any form of light pollution, including moonlight. On the opposite side of the sky from the sun, you might even catch a glimpse of something called the Gegenschein, or counterglow. This is an extremely faint brightening of the sky that occurs when you're looking directly away from the sun, caused by sunlight backscattering off interplanetary dust particles. It's like seeing the shadow of Earth cast on the cosmic dust that fills our solar system. The meteor showers that occur throughout the year would become dramatically more spectacular without the moon's interference. Meteor showers like the Perseids in August, the Geminids in December, and the Leonids in November would display their full glory against the dark sky background. These shooting stars are caused by Earth passing through streams of debris left behind by comets as they orbit the sundial. When these tiny particles, most no larger than grains of sand, enter Earth's atmosphere at speeds of up to 160,000 miles per hour, they burn up and create those brilliant streaks of light we call meteors. Without moonlight washing out the fainter meteors, you'd see not just the bright fireballs that are visible even on moonlit nights, but also the dozens of dimmer meteors that normally go unnoticed. During peak meteor shower nights, you might observe 60 to 100 meteors per hour instead of the 20 to 30 you'd typically see with the moon shining. The planets would also take on a different character in our moonless sky. Venus, Mars, Jupiter, and Saturn would still be the brightest objects after the sun, but their relative prominence would increase dramatically. Jupiter's four largest moons, Io, Europa, Ganymede, and Callisto, would be easier to spot with binoculars or a small telescope, as they wouldn't be competing with moonlight for contrast. Saturn's rings would appear more dramatic through telescopes, and the planet's largest moon, Titan, would be more readily visible. Mars, during its opposition periods when it's closest to Earth, would show more surface detail through telescopes due to the improved contrast against the darker sky background. But perhaps the most profound change would be in how we experience and understand our place in the universe. The overwhelming presence of the Milky Way stretching across the entire sky would serve as a constant reminder that we're living on a small planet orbiting an ordinary star in the outer regions of a galaxy containing hundreds of billions of other stars. This perspective shift has psychological and philosophical implications that are hard to overstate. Indigenous cultures around the world have rich traditions of navigation, timekeeping, and mythology based on detailed knowledge of the night sky. The Aboriginal Australians have songlines that map the landscape using star patterns. The Polynesian navigators crossed thousands of miles of open ocean using only the stars as their guide. In a hypothetical moonless world, these skills and traditions would likely be even more developed because the increased visibility of stars would provide more navigation points and more detailed celestial maps. The human relationship with the cosmos would necessarily be more intimate and immediate. The seasonal changes in the night sky would also be more apparent. As Earth orbits the sun, different portions of the Milky Way become visible at different times of year. In summer, observers in the northern hemisphere see toward the galactic center, which appears as the brightest and most dense part of the Milky Way. In winter, we see away from the galactic center toward the outer edge of the galaxy where stars are more sparse. These seasonal variations would be much more obvious without moonlight interference, creating a kind of cosmic calendar that's directly visible to anyone who spends time outdoors at night. The rising and setting times of different star patterns would serve as natural markers for planting seasons, migration patterns, and cultural celebrations. The absence of the moon would also affect the behavior of nocturnal animals in ways that would ripple through entire ecosystems. Many animals use moonlight for navigation, hunting, and mating behaviors. Sea turtles navigate by moonlight, reflecting off the ocean. Many species of moths and other insects are confused by artificial lights because they've evolved to use the moon as a navigation reference. Predator-prey relationships would shift dramatically. Animals that currently hunt during the darkest nights when there's no moon would have a significant advantage every single night. Conversely, prey animals that rely on moonlight to spot approaching predators would be at a constant disadvantage. The reproductive cycles of countless species are tied to lunar phases. Coral reefs spawn in synchronized events timed to specific moon phases. Many fish species time their spawning to lunar cycles. The removal of the moon would disrupt these ancient biological rhythms that have evolved over millions of years. But let's dig deeper into the astronomical implications of our moonless scenario. The absence of our large satellite would reveal not just more stars and galaxies, but also transient astronomical events that are normally difficult to observe due to moonlight interference. Supernovae, the explosive deaths of massive stars, would be more easily spotted by amateur astronomers. These stellar explosions can briefly outshine entire galaxies, but many go unnoticed because they occur in regions of sky that are washed out by moonlight or light pollution. In our moonless world, dedicated sky watchers would be much more likely to discover these cosmic catastrophes as they happen. Variable stars, which change in brightness over periods ranging from hours to years, would be more easily monitored. These stars include pulsating giants that expand and contract like cosmic hearts, binary systems where one star periodically eclipses another, and cataclysmic variables where material from one star falls onto a compact companion, causing unpredictable flares and explosions. The aurora borealis and aurora australis, the northern and southern lights, would be dramatically more visible and impressive without lunar interference. These dancing curtains of light are caused by charged particles from the solar wind interacting with Earth's magnetic field and atmosphere. The colors, greens, reds, blues, and purples, are created by different atmospheric gases being excited at different altitudes. Currently, aurora displays are often overwhelmed by moonlight, especially the fainter red and blue emissions that occur at higher altitudes. In our moonless world, aurora would frequently fill large portions of the sky with shimmering, moving light, shows that would be visible much further from the polar regions than they are today. The solar system's smaller bodies would also become more apparent. Asteroids, which are normally too faint to see without telescopes, might occasionally become visible to the naked eye during particularly close approaches to Earth. Comets, those dirty snowballs from the outer solar system, would display their tails more dramatically against the darker sky background. When comets develop their characteristic tails as they approach the sun and their icy surfaces begin to sublimate, these tails can extend for millions of miles through space. The dust tail, composed of particles blown away from the comet's nucleus by solar radiation pressure, and the gas tail, made of ionized molecules pushed away by the solar wind, would both be more easily visible without moonlight competition. The phenomenon of comet tail orientation would become more obvious to casual observers. Both types of tails always point away from the sun, regardless of the comet's direction of motion. This means that as a comet approaches the sun, it leads with its nucleus and the tail follows behind. But as it swings around the sun and heads back to the outer solar system, the tail actually precedes the nucleus, like a cosmic streamer being pulled along. Deep sky objects that are currently the exclusive domain of telescopic observation would become naked eye targets. The Orion Nebula, already faintly visible to sharp-eyed observers under dark skies, would become an obvious cloud-like patch in the Sword of Orion. This stellar nursery, where new stars are currently being born about 1,300 light-years away, would display its complex structure of gas and dust illuminated by hot, young stars. The Pleiades star cluster, also known as the Seven Sisters, would reveal not just its 7 brightest stars, but potentially dozens of its fainter members. This open cluster contains over 1,000 stars, all born from the same giant cloud of gas and dust about 100 million years ago. The nebulosity surrounding the stars, caused by the cluster passing through an unrelated dust cloud, would be more easily visible as a subtle blue reflection nebula. Other open clusters like the Beehive cluster in Cancer and the double cluster in Perseus would become obvious naked eye objects, appearing as fuzzy patches that resolve into individual stars when viewed through binoculars. These stellar associations represent different stages of cluster evolution, from young, hot blue stars that haven't yet drifted apart to older clusters where the original member stars have begun to disperse throughout the galaxy. Globular clusters, those dense spherical collections of hundreds of thousands of ancient stars, would become more prominent features of the night sky. The brightest globular clusters, like Omega Centauri and 47 Tucanae, would be easily visible as fuzzy star-like objects. These stellar cities contain some of the oldest stars in our galaxy, formed over 10 billion years ago when the Milky Way was still young and actively consuming smaller galaxies. The seasonal progression of constellations would become a more integrated part of human culture and daily life. Currently, many people in urban environments lose track of the seasonal changes in the night sky because they rarely see enough stars to notice the patterns. In our moonless world, the rising of specific constellations would mark seasonal transitions in an immediate, visceral way. The summer triangle formed by the stars Vega, Altair, and Deneb would dominate summer skies, with each star representing a different distance scale. Vega, at 25 light-years away, is relatively close to us. Altair, at 17 light-years, is even closer. But Deneb, despite appearing similar in brightness to the other two, is actually over 2,000 light-years away and is one of the most luminous stars known in our galaxy. Winter would bring Orion, perhaps the most recognizable constellation in the night sky, along with its entourage of surrounding constellations. The winter sky actually contains more bright stars than any other season, making it particularly spectacular. Sirius, the brightest star in the night sky, would be even more prominent without lunar interference. This binary star system, with a white dwarf companion orbiting the main sequence star, sits just 8.6 light-years away and serves as a benchmark for stellar brightness measurements. Spring would usher in the realm of galaxies, as the Milky Way's plane tilts away from the evening sky and allows clear views into intergalactic space. The Virgo cluster, a collection of over 1,300 galaxies located about 65 million light-years away, might become detectable to dedicated observers using large binoculars. This galaxy cluster is part of the larger Virgo supercluster, which includes our own local group of galaxies. The autumn sky would bring back the rich star fields of the Milky Way, but from a different angle than summer provides. The constellations of Pegasus, Andromeda, and Perseus would frame views toward the anticenter of our galaxy, revealing different spiral arm structures and stellar populations than those visible during summer months. But our exploration of the moonless night sky must also consider the profound changes that would occur to Earth itself without our large satellite's gravitational influence. The moon's gravity doesn't just cause ocean tides, it also creates tiny but measurable deformations in the solid Earth itself. These Earth tides cause the planet's surface to rise and fall by as much as 20 inches twice per day, though this motion is imperceptible to human senses. Without the moon's gravitational influence, Earth's rotation would gradually speed up over millions of years. Currently, tidal friction caused by the moon's gravity is gradually slowing Earth's rotation and causing our days to become slightly longer over time. When the moon first formed, roughly 4.5 billion years ago, Earth was spinning much faster, with days lasting only about 6 hours. In our moonless scenario, Earth's rotation rate would depend on its initial conditions, but without the stabilizing influence of a large satellite, the planet's rotational axis would become chaotic over long periods. Currently, the moon's gravity helps stabilize Earth's axial tilt at approximately 23.5 degrees, which is responsible for our regular seasonal cycles. Without this stabilization, Earth's axis would wobble unpredictably over periods of millions of years, sometimes tilting much more than it currently does, sometimes much less. During periods of high tilt, the polar regions would receive much more direct sunlight during their respective summers, while the equatorial regions might become relatively cooler. During periods of low tilt, the temperature difference between seasons would be minimized, but the difference between equatorial and polar temperatures would be maximized. These chaotic variations in axial tilt would create climate instabilities that would make the evolution of complex life much more challenging. The stable, predictable seasons that have characterized Earth's climate for hundreds of millions of years are partly due to the moon's stabilizing influence on our planet's rotation. The ocean tides, which currently rise and fall twice per day due to the moon's gravity, would be much smaller and would be caused entirely by the sun's gravitational pull. Solar tides are about 46% the strength of lunar tides, so the combined tides we experience today would be replaced by much gentler solar tides alone. This would have profound implications for coastal ecosystems, which have evolved to take advantage of the daily rhythm of tidal exposure and submersion. Intertidal zones, those areas between high and low tide marks, support some of the most diverse and productive ecosystems on Earth. Many marine organisms time their feeding, reproduction, and other behaviors to tidal cycles. The reduced tidal range would also affect coastal geology. The constant action of tides helps shape coastlines, move sediments, and create features like barrier islands and tidal marshes. Without strong tides, coastal environments would be much more static, potentially leading to different patterns of erosion and sediment deposition. River systems that currently experience tidal bores, where incoming tides create waves that travel upstream against the river's flow, would lose this dynamic feature. The Amazon River's tidal bore, known as the pororoca, can create surfable waves that travel hundreds of miles upstream. These phenomena help oxygenate river water and distribute nutrients throughout river delta systems. The biological implications extend far beyond marine ecosystems. Many terrestrial animals have evolved behaviors that are synchronized with lunar cycles, even though the adaptive advantage isn't always obvious. Studies have shown correlations between lunar phases and the timing of births in various mammalian species, though the mechanisms behind these correlations aren't fully understood. Human biology also shows some intriguing connections to lunar cycles, though these are often controversial and not always reproducible in scientific studies. Some research suggests correlations between lunar phases and sleep quality, menstrual cycles, and even hospital admission rates, though the evidence remains mixed and the mechanisms unclear. What isn't controversial is the cultural and psychological impact the moon has had on human civilization. The lunar calendar forms the basis for many religious and cultural traditions. The Islamic calendar is purely lunar, with months beginning at the new moon. The Jewish calendar is lunisolar, incorporating both lunar months and solar year corrections. Even the Christian calculation of Easter depends on lunar phases, being set as the first Sunday after the first full moon occurring on or after the spring equinox. In our moonless world, these calendar systems would never have developed. Instead, human timekeeping would likely be based entirely on solar observations and stellar positions. This might lead to more precise solar calendars being developed earlier in human history, but it would also mean losing the convenient monthly divisions that the lunar cycle provides. The psychological impact of losing the moon extends beyond calendar systems. The moon has been a source of inspiration for poets, artists, and lovers throughout human history. The romantic notion of moonlit nights, the mystical associations with lunar phases, the use of the moon as a symbol for femininity, change, and cycles of death and rebirth, all of these cultural elements would be absent from human consciousness. Instead, the night sky would be dominated by the grand sweep of the Milky Way, which might take on many of the symbolic roles currently occupied by the moon. The galactic center, with its dense concentration of stars, might become associated with concepts of unity, centrality, or divine presence. The dark dust lanes that create patterns within the Milky Way might be seen as cosmic rivers, roads, or the shadows of celestial beings. Different cultures would likely develop rich mythologies around the various bright stars and constellations that would be much more prominent without lunar interference. The Southern Cross, which is currently used for navigation by Southern Hemisphere cultures, would be even more significant as a celestial landmark. The pointer stars, Alpha and Beta Centauri, would be recognized as the nearest star system to our Sun, with Alpha Centauri being a triple star system located just 4.37 light-years away. The concept of navigation would be fundamentally different in our moonless world. Currently, the moon serves as a primary navigation reference for many purposes, especially at sea. Its phases provide rough timing information, and its position relative to the horizon can indicate direction. Without the moon, navigation would rely much more heavily on stellar positions and the movement of planets. This would likely lead to earlier and more sophisticated development of astronomical knowledge. Ancient civilizations would need to develop detailed star charts and understand stellar motions much earlier in their development, simply to navigate effectively. The precession of the equinoxes, the slow 26,000-year wobble of Earth's axis that causes the positions of stars to shift relative to the calendar, would be discovered much earlier because precise stellar navigation would be essential. The absence of moonlight would also affect the development of artificial lighting technology. Historically, humans have supplemented natural lighting with fires, oil lamps, candles, and eventually electric lights. In a world where every night is significantly darker, the development of artificial lighting might have proceeded more quickly, or perhaps humans would have adapted to be more active during daylight hours. Alternatively, human night vision might have evolved to be significantly better than it currently is. Our eyes are actually quite poor at seeing in low light conditions compared to many other mammals. Cats, for example, need only 1/6 as much light as humans to see effectively. In a world without moonlight, there would be significant evolutionary pressure for improved night vision, potentially leading to humans with larger eyes, different pupil structures, or more light-sensitive retinas. The social implications of perpetually darker nights are fascinating to consider. Currently, many cultures have traditions and activities associated with full moon nights, festivals, hunting expeditions, romantic encounters, and spiritual ceremonies. The regular rhythm of bright and dark nights provided by lunar phases creates natural cycles for different types of activities. Without this rhythm, social activities would need to be organized around different cycles. Perhaps seasonal festivals would become more important, timed to the rising and setting of particular star patterns. Maybe the appearance of specific comets or meteor showers would become major cultural events, anticipated and celebrated across generations. The development of astronomy as a science would likely proceed along different lines. Currently, many amateur astronomers schedule their observations around the new moon phases, when the sky is darkest. Professional observatories often plan their most sensitive observations during moonless periods. In our hypothetical world, every night would be optimal for astronomical observation, which might lead to much more rapid advances in our understanding of the universe. The discovery of galaxies, nebulae, and other deep sky objects would probably occur much earlier in human history, simply because they would be visible to anyone who looked up on a clear night. The realization that the Milky Way is just one galaxy among billions might come centuries earlier than it did in our timeline. This earlier cosmic perspective might have profound implications for the development of philosophy, religion, and science. The awareness of our place in a vast universe filled with billions of other galaxies would be immediate and obvious, rather than a recent scientific discovery that many people still struggle to fully comprehend. Now here's where things get really incredible. Let me paint you a picture of exactly what you'd witness if you could step outside right now into a world without the moon. It's about 10 p.m. on a clear night. You walk out your door and immediately notice something feels different. The ambient light level is dramatically lower than anything you've experienced before. There are no street lights in this scenario, no city glow, nothing but the natural darkness that has been Earth's nighttime reality for billions of years. Your eyes begin to adjust, and within the first few minutes, you start to see more stars than you've ever seen in your life. But this is just the beginning. As your pupils dilate fully and your retinal chemistry shifts into maximum sensitivity mode, the real show begins. After about 15 minutes, you notice something extraordinary starting to emerge in the sky. What looked like empty space between the familiar constellations is filling in with a soft, ethereal glow. This is the Milky Way beginning to reveal itself, and it's unlike anything you could have imagined. The galactic band starts as a subtle brightening, like the faintest possible cloud stretched across the entire dome of the sky. But as your eyes continue to adjust, this glow intensifies and develops structure. Dark lanes begin to appear within the light, creating complex patterns that look almost like a cosmic river system viewed from above. By 30 minutes, your eyes have reached their full dark adaptation potential, and the sky has been completely transformed. The Milky Way now dominates everything, stretching from horizon to horizon as a luminous pathway that seems to have depth and texture. You can see variations in brightness and color throughout its length, from the dim outer regions to the brilliant central bulge. Looking towards Sagittarius, where the galactic center lies, the Milky Way appears to widen and brighten dramatically. This region, which is normally completely invisible to city dwellers and barely perceptible even under rural skies with moonlight, now appears as a glowing cosmic metropolis. The concentration of stars is so dense that individual points of light merge into patches of soft luminescence. The dark lanes that create patterns within the Milky Way become clearly defined features. The Great Rift, a dark cloud complex that appears to split the Milky Way in two, stretches from Cygnus down through Aquila and into Sagittarius. This isn't empty space. It's enormous clouds of dust and gas that block the light from millions of stars behind them. These dust clouds have shapes and personalities of their own. The Coal-Sack Nebula near the Southern Cross appears as a dark patch against the bright star fields. The Snake Nebula winds its way through the constellation Ophiuchus like a cosmic serpent. The Dark Horse Nebula rears up near Antares, creating the silhouette of a horse's head against the stellar background. But the dark features are just one part of the show. Bright nebulae begin to pop out as obvious naked-eye objects. The Lagoon Nebula and the Trifid Nebula in Sagittarius appear as distinct patches of light with subtle color variations. The Eagle Nebula and the Swan Nebula become obvious features of the galactic plane. In the constellation Orion, the Great Nebula becomes a spectacular sight. No longer just barely visible to keen eyes, but clearly defined as a cloud-like structure surrounding the stars of Orion's sword. The subtle colors of the nebula, the reds from hydrogen emission and the blues and greens from reflected starlight, become apparent to your dark-adapted eyes. The individual stars themselves take on new character. Stars that you never knew existed become obvious members of familiar constellation patterns. The Big Dipper, instead of having 7 stars, might appear to have dozens of stars creating a complex ladle shape. Orion's belt isn't just 3 stars, but a rich stellar association with countless fainter members. The brightness variations between stars become much more apparent. You can easily distinguish between the blue-white giants, the yellow sun-like stars, the orange giants, and the red supergiants by their colors. Betelgeuse, the red supergiant in Orion's shoulder, glows with an obviously reddish tint. Rigel, the blue supergiant in Orion's foot, shines with brilliant blue-white light. Double and multiple star systems that are normally invisible become resolved to your naked eye. Alboreo in Cygnus reveals itself as a beautiful gold and blue double star. The stars of the Big Dipper's handle show their various colors and brightness differences more clearly. About an hour into your observation, as your eyes reach peak sensitivity, you begin to notice the other galaxies. The Andromeda Galaxy, normally just barely visible as a fuzzy patch, now appears as an obvious oval glow spanning several degrees of sky. You can make out structure within the galaxy, the bright central bulge and hints of the spiral arms. If you're observing from the southern hemisphere, the large and small Magellanic clouds become prominent features of the sky, appearing as bright, irregular patches that are clearly separate from the Milky Way. These satellite galaxies show complex internal structure, with dark lanes, bright star-forming regions, and different colors throughout their extent. The Triangulum Galaxy becomes visible as a large, faint spiral structure. Even more remarkably, other galaxies in the local group might become barely detectable, pushing the absolute limits of naked eye visibility, but occasionally glimpsed by the most keen-eyed observers under perfect conditions. As you continue watching, you notice that the sky isn't static. The stars are slowly wheeling overhead as Earth rotates, but more immediately noticeable are the meteors. Without moonlight interference, you're seeing every meteor that enters the atmosphere with enough energy to create a visible streak. Instead of the 1 or 2 meteors per hour you might normally notice, you're seeing dozens. These aren't just the bright fireballs that are visible even on moonlit nights. You're seeing the faint streaks created by particles no bigger than grains of sand. Some, last for just a fraction of a second. Others persist for several seconds as they burn up in the atmosphere. Occasionally, you witness a brilliant fireball that lights up the entire landscape for a moment, leaving a glowing train that persists for minutes. If you're lucky enough to be observing during a meteor shower, the display is absolutely spectacular. During the peak of the Perseids or Geminids, you might see a meteor every minute or two, with occasional periods where multiple meteors appear simultaneously, creating a celestial fireworks display. The planets, when they're visible, take on enhanced prominence against the darker sky background. Venus, when it appears as the evening or morning star, is brilliant enough to cast shadows. Jupiter shows its distinct yellowish color more clearly, and through binoculars, its four largest moons are easily spotted as tiny points of light aligned with the planet's equator. Mars, during its opposition periods, glows with an unmistakable reddish color that makes its identity obvious even to casual observers. Saturn's golden hue becomes apparent, and through a small telescope, the rings are clearly visible with much better contrast than they would have against a moonlit sky. The zodiacal light, that triangular glow extending along the ecliptic, becomes a prominent feature of the pre-dawn and post-sunset sky. This ethereal pyramid of light stretches upward from the horizon, following the path that the sun and planets trace across the sky. It's caused by sunlight scattering off countless tiny dust particles that orbit the sun in the same plane as the planets, the remnants of comet tails and asteroid collisions that have been ground down over billions of years into microscopic debris. What makes the zodiacal light particularly magical in our moonless world is how it connects the terrestrial landscape with the cosmic environment. As the glow rises from the horizon, it creates a bridge between the familiar silhouettes of trees, mountains, or buildings and the star-filled dome above. The light has a soft, almost ethereal quality that's completely different from the harsh brightness of artificial lighting or even moonlight. During certain times of year, when the ecliptic makes a steep angle with the horizon, the zodiacal light can extend more than halfway up the sky. In spring evenings and autumn mornings, it becomes one of the most prominent features of the twilight sky, rivaling even bright planets in its visual impact. But the truly mind-bending moment comes when you realize what you're actually seeing. Every photon of light hitting your eyes has traveled 93 million miles from the sun, bounced off a particle of dust somewhere in the inner solar system, and then traveled to your location on Earth. You're seeing sunlight that has taken a detour through the cosmic debris field that surrounds our star. As your observation session continues into the deeper hours of the night, you begin to notice phenomena that are completely invisible in our current moon-influenced world. The Gegenschein, or counterglow, appears as a subtle brightening of the sky directly opposite the sun's position. This incredibly faint glow is visible only under the darkest conditions and represents backscattered sunlight from dust particles in the outer regions of the zodiacal cloud. The Gegenschein is so faint that it's barely brighter than the background sky, but once you learn to see it, it becomes an obvious feature. It appears as an oval patch of light, roughly the size of your outstretched hand, located at the anti-solar point, the spot in the sky directly opposite the sun. As the night progresses and the anti-solar point moves across the sky, the Gegenschein moves with it, creating a gentle, luminous presence that follows a predictable path. During the hours around midnight, when the anti-solar point is highest in the sky, the Gegenschein reaches its most prominent position. At this point, you're looking directly away from the sun through the thinnest portion of Earth's atmosphere, at dust particles that are backscattering sunlight directly toward you. It's like seeing Earth's shadow projected onto the cosmic dust that fills our solar system. The interplay between the zodiacal light and the Gegenschein creates something called the zodiacal band, a faint glow that can sometimes be traced all the way around the sky, following the ecliptic from the zodiacal light in the west through the Gegenschein at the anti-solar point and connecting to the zodiacal light rising in the east before dawn. This complete circuit of reflected sunlight reveals the three-dimensional structure of the dust cloud that surrounds our star. As the night reaches its darkest hours, typically between 2 and 4 a.m., your eyes achieve their absolute peak sensitivity. This is when the most subtle features of the night sky become visible. Star clusters that appeared as fuzzy patches earlier in the evening now resolve into collections of individual stars. Nebulae show more structure and detail. The spiral arms of the Milky Way become more clearly defined. The colors of stars become particularly apparent during these peak darkness hours. The temperature of a star determines its color, and without any competing light sources, these color differences become obvious even to casual observation. The hottest stars shine with brilliant blue-white light, while the coolest red giants glow with distinctly reddish hues. The sun-like yellow stars occupy the middle ground, with orange giants showing intermediate colors. Double star systems reveal their true nature during peak darkness. Stars that appear single to the unaided eye under normal conditions might show as obviously double objects when viewed without any light pollution. The famous double star Albareo in Cygnus becomes a stunning golden blue pair that looks almost like a tiny pair of colored headlights in the sky. Multiple star systems become even more interesting. The trapezium in Orion, normally requiring a telescope to resolve, might show hints of its four-star structure to exceptionally keen eyes under perfect conditions. These stellar nurseries, when new stars are being born from collapsing gas clouds, take on added significance when you can actually see the individual stellar embryos. The seasonal progression of the sky becomes a natural timekeeper in our moonless world. As the hours pass and Earth's rotation carries different star patterns overhead, you witness the same stellar motion that has served as humanity's clock for thousands of years. The rising of specific stars and constellations has historically marked everything from planting seasons to religious festivals. In late evening, the summer constellations dominate the sky in their full glory. The summer triangle formed by Vega, Altair, and Deneb spans huge portions of the sky, with each star representing a different chapter in stellar evolution. Vega, relatively close and stable, represents stars in their prime. Altair, also nearby, spins so rapidly that it's noticeably flattened at its poles. Deneb, incredibly distant and luminous, is a supergiant star that will eventually explode as a supernova. As the night progresses toward dawn, the autumn constellations rise in the east. Pegasus, the great square that serves as a landmark for finding other autumn stars, appears above the horizon. Andromeda, containing our nearest galactic neighbor, climbs higher into the dark sky. Perseus, with its variable star Algol that brightens and dims every 2.9 days, adds to the stellar theater. The progression continues with winter constellations making their appearance before dawn. Orion, that magnificent stellar showcase, rises in the east with all its accompanying star patterns. The winter sky contains more bright stars than any other season, creating a brilliant display that would be absolutely spectacular in our moonless world. Each constellation carries not just its visible stars, but also its deep sky treasures. Orion brings not just the Great Nebula, but also the Horsehead Nebula, the Flame Nebula, and numerous star clusters. Cassiopeia reveals heart-shaped nebulae and the remnants of ancient supernovae. Cygnus displays the North America Nebula and the Veil Nebula, vast shells of gas blown off by exploding stars. The changing position of the Milky Way throughout the night adds another layer to the celestial show. In early evening, the galactic center is highest in the sky, showing the richest star fields and most prominent dust lanes. As the night progresses, different sections of our galaxy wheel overhead, each revealing different stellar populations and structures. The outer regions of the galaxy, visible when looking away from the center, show a different character entirely. The star density is lower, but individual stars and star clusters become more prominent. The Pleiades, that jewel box of blue stars, appears as an obvious fuzzy patch that resolves into dozens of individual points of light when viewed through binoculars. Globular clusters become prominent features scattered around the sky. These ancient stellar cities, containing hundreds of thousands of stars in spherical arrangements, appear as fuzzy, star-like objects to the naked eye but explode into incredible detail when viewed through telescopes. Each globular cluster represents a relic from the early universe, formed when our galaxy was young and actively consuming smaller companion galaxies. The variable stars scattered throughout these constellations add a dynamic element to the sky. Stars like Mira and Cetus change dramatically in brightness over periods of months, sometimes becoming easily visible to the naked eye, other times fading below the threshold of naked eye visibility. These pulsating giant stars are in the final stages of their lives, throwing off their outer layers in preparation for becoming white dwarf stars. Eclipsing binary systems create their own rhythm of brightness changes. Algol in Perseus dims noticeably every 2.9 days as one star passes in front of its companion. Beta Lyrae varies continuously as its two component stars orbit each other in a complex dance of gravitational interaction. These stellar partnerships reveal the dynamic nature of star systems and the complex gravitational relationships that exist throughout our galaxy. As dawn approaches and the first hints of sunlight begin to brighten the eastern horizon, the most dedicated observers might catch a glimpse of the zodiacal light rising before the Sunday. This morning, zodiacal light often appears more prominent than its evening counterpart, especially during autumn months when the ecliptic makes a steep angle with the morning horizon. The transition from night to dawn in our moonless world would be particularly dramatic. Without the gradual brightening that moonset provides in our current world, the contrast between deep night and the first signs of dawn would be sharp and sudden. The zodiacal light would be the first herald of the approaching sun, followed by the gradual brightening of the eastern sky that marks the beginning of astronomical twilight. During astronomical twilight, when the sun is between 12 and 18 degrees below the horizon, the brightest stars and planets remain visible while the sky gradually brightens. This is often considered the most beautiful time for sky observation, as the subtle glow of the brightening sky provides just enough illumination to reveal landscape features while still allowing the brightest celestial objects to shine through. The progression through nautical twilight, when the sun is between 6 and 12 degrees below the horizon, marks the end of serious astronomical observation but provides its own unique viewing opportunities. The brightest planets and stars create stunning contrasts against the gradually brightening sky. Venus, when visible, becomes particularly spectacular during this time, often appearing bright enough to see in full daylight if you know exactly where to look. The final stage of twilight, civil twilight, occurs when the sun is less than 6 degrees below the horizon. At this point, only the very brightest celestial objects remain visible, but the interplay between the brightening sky and these brilliant points of light creates some of the most photographically stunning moments of the entire night-to-day transition. Throughout this entire nocturnal journey, from the first emergence of stars in the deepening twilight to their final disappearance in the dawn, You would have experienced a connection with the cosmos that's been largely lost to modern civilization. The overwhelming presence of the Milky Way, the obvious visibility of other galaxies, the rich tapestry of star colors and brightness variations, and the dynamic nature of meteors and variable stars would create a night sky experience that's almost impossible to imagine from our current light-polluted, moon-influenced perspective. The psychological impact of spending an entire night under such a sky would be profound and lasting. The immediate, visceral understanding of your place in the universe that comes from seeing the galaxy spread out above you is something that no amount of reading or theoretical knowledge can provide. It's the difference between knowing intellectually that you live in a vast cosmos and feeling that reality in your bones. Indigenous cultures around the world developed rich astronomical traditions, partly because they had regular access to skies similar to what we've been describing. The Australian Aboriginal songlines that map the continent using star patterns, the Polynesian navigation techniques that guided voyagers across thousands of miles of open ocean, the agricultural calendars of ancient civilizations that were precisely tuned to stellar positions. All of these cultural achievements were possible because people had intimate, nightly familiarity with the detailed structure of the night sky. In a hypothetical moonless world, these astronomical traditions would likely be even more sophisticated and widespread. The increased visibility of celestial objects and phenomena would make astronomical knowledge not just useful, but absolutely essential for navigation, timekeeping, and seasonal planning. Every culture would necessarily develop detailed star maps and understanding of celestial motions. The development of scientific astronomy would also proceed along different lines. Many of the fundamental discoveries about the nature of stars, galaxies, and cosmic distances were delayed in our timeline because the objects in question were too faint to study effectively with early telescopes. In a world where galaxies, nebulae, and star clusters were obvious naked-eye objects, these discoveries would likely occur much earlier in human history. The philosophical implications of having constant access to such cosmic vistas are hard to overstate. The awareness that we live in a universe containing billions of other galaxies, each with billions of stars, would be immediate and obvious, rather than a recent scientific discovery that many people still struggle to internalize. This cosmic perspective might lead to very different developments in philosophy, religion, and our understanding of humanity's place in the universe. The practical implications would extend into every aspect of human culture. Architecture might develop differently, with more emphasis on observatories and sky viewing platforms. Agriculture would be more precisely tuned to stellar calendars. Art and literature would be filled with detailed references to specific star patterns and cosmic phenomena that are currently known only to dedicated astronomers. Music might incorporate the rhythms of variable stars or the timing of meteor shower peaks. Poetry would be rich with imagery drawn from the detailed structure of the Milky Way, the colors of different stellar types, and the seasonal progression of constellation patterns. The human relationship with the natural world would necessarily include this cosmic dimension in a way that's largely absent from modern culture. But perhaps the most significant difference would be in how we understand time and change. Currently, most people experience the night sky as relatively static. The same patterns of stars appearing night after night, season after season, with only the moon and planets showing obvious motion. In our moonless world, the dynamic nature of the cosmos would be much more apparent. Variable stars changing in brightness, meteors streaking across the sky, the Milky Way rotating overhead with the seasons, the slow procession of star positions over years and decades. All of these would be obvious features of the night sky experience. This would create a much more dynamic understanding of the universe as a place where change is constant and visible. The concept of deep time, the vast scales of years and millennia over which cosmic changes occur, would be more intuitive because people would directly observe stellar changes happening over human timescales. The variable star cycles, the precession of stellar positions, the changing visibility of comets and meteor showers would all serve as natural chronometers marking the passage of cosmic time. So, what started as a simple question about removing the moon from our night sky has taken us on a journey through stellar evolution, galactic structure, human culture, and the fundamental relationship between Earth and the cosmos. The absence of our satellite would reveal not just more stars and galaxies, but an entirely different human relationship with the universe around us. Without the moon's reflected sunlight washing out the night sky, we would see thousands more stars with our naked eyes. The Milky Way would dominate every clear night, stretching from horizon to horizon as a luminous river of starlight, punctuated by dark dust lanes and bright stellar neighborhoods. Other galaxies would be obvious features of the night sky, and phenomena like the zodiacal light and Gegenschein would be familiar sights to anyone who spent time outdoors after dark. The seasonal progression of constellations would serve as a natural calendar, more precise and obvious than any human timekeeping system. Variable stars would provide visible demonstrations of stellar evolution happening on human timescales. Meteor showers would be spectacular displays of cosmic debris burning up in our atmosphere. But the changes would extend far beyond what we could see. Earth's rotation would be faster and less stable without the moon's gravitational influence. Ocean tides would be much weaker, affecting coastal ecosystems and geological processes. The biological rhythms of countless species that are synchronized to lunar cycles would be disrupted. Human culture would develop along entirely different lines, with astronomical knowledge being essential rather than specialized. Navigation, agriculture, and timekeeping would all be intimately connected to detailed understanding of stellar positions and motions. Philosophy and religion would be shaped by the immediate, overwhelming presence of cosmic vistas that make our place in the universe impossible to ignore. The psychological impact of living under such skies would create a fundamentally different relationship between humanity and the cosmos. Instead of feeling separate from or disconnected from the universe, people would have a visceral, nightly reminder that we are embedded in a vast cosmic structure that extends far beyond our planet. This moonless world would be a place where the boundary between Earth and space feels much more permeable, where the cosmic perspective is not an abstract intellectual concept, but a lived daily experience. It would be a world where looking up at the night sky provides not just beauty and wonder, but immediate connection to the deepest structures and longest timescales in the universe. The trade-offs would be significant. Losing the moon's role in stabilizing our planet's climate and rotation, losing the tidal rhythms that have shaped life on Earth, losing the cultural and romantic associations that the moon has provided throughout human history. But the compensation would be unprecedented access to cosmic vistas that reveal the true scale and beauty of the universe we inhabit. In the end, imagining the night sky without the moon helps us appreciate both what we have and what we're missing. Our actual night sky, with its monthly cycle of bright and dark periods, provides a rhythm and variety that a permanently dark sky would lack. But it also hides cosmic wonders that most of humanity has never experienced and may never see. The next time you look up at the moon, remember that its gentle glow is simultaneously one of the most beautiful sights in our sky and one of the greatest obstacles to seeing the deeper universe beyond. In that silver light lies both a gift and a veil. illuminating our world while hiding the greater cosmos that surrounds us. If this cosmic journey has sparked your curiosity about what lies hidden in our own night sky, step outside tonight and see how much you can discover for yourself.